Cool. Let's talk a little bit about cholesterol. I won't spend a huge amount of time here. We learned about cholesterol as one of the other forms of lipids earlier in the semester, way back in the early days of the semester when life seemed so much easier, right? You still want to recognize the structure of cholesterol here. So see the 4 rings. So both cholesterol or anything related to cholesterol. So can he expect you to draw this structure out? Probably not, but I can't guarantee it, but I would say that's probably diminishing returns there at that point. But here's the synthesis of cholesterol. So it actually starts with HMG-CoA, which we saw a little bit earlier as part of ketogenesis. HMG-CoA reductase reduces it to mevalonate. And if I'm going to reduce it, what has to happen simultaneously? Oxidation. In this case, NADPH is oxidized. It takes 2 molecules. So if you notice, NADPH to NADP plus is a 2-electron process. If I have to use 2 NADPHs up here, that's a 4-electron process. That's actually 2 steps of oxidation. And if you notice, we are going from, in this case, a thioester, which is the equivalent of a carboxylate in terms of oxidation, so all the way to an alcohol, and that is indeed 2 steps of reduction, which is why it required 2 NADPHs getting oxidized to happen. Mevalonate is then converted into IPPP. These structures are probably worth knowing, I'm sorry to tell you. They're small molecules. I can't guarantee that, it would come up, but again, when I see small molecules, I think, he could ask that, darn it. So, and again, he might not, but they might be worth knowing. IPP, notice you can see a bunch of these IPPs get incorporated to make squalene here. So in squalene then goes through a 22 enzymatic step process to become cholesterol. 22 steps. Good times. Cool. I don't think necessarily knowing scaling structure or necessarily being able to draw out cholesterol is the most important. But when I see these small molecules again, and the fact that this is the second time we've seen HMG-CoA, might not be the worst one in the world to know. So cholesterol. If we look at cholesterol degradation, so if you have too much cholesterol, you can turn into bile salts. What are bile salts? Where do you find them? Liver. Where's your liver send bile salts? To the gallbladder, and the gallbladder then transfers them to your small intestine. What are they used for? Break down fat. Break down fat. So the reason they're good at breaking down fat is that they're both hydrophobic with all these carbons and hydrogens, and then hydrophilic with the hydroxyl groups and the carboxylate. So the same way that soaps are both hydrophobic and hydrophilic and can wash away dirt and oils, but bind the water to be washed away. So same kind of purpose here. So it can hydrolyze the fats, or I shouldn't say hydrolyze, emulsify is the word we like to use, emulsify the fats. So I have a friend who does a cleansing diet every once in a blue moon, and she will go without a whole lot of food for like 3 days. And then she will drink like a 1/4 cup of olive oil. Yeah, I know, it doesn't sound good to me either. So, I mean, I'll drink olive oil before Crisco, right? But olive oil, ugh. So, but the idea is that she starved herself, and now all of a sudden with this overload of fat, and it's not the worst fat in the world, right? But this overload of fat, now all of a sudden, your body's like, whoa, we are now needing to emulsify a boatload of fat, eject a boatload of bile salts. So, and it's a way of apparently cleaning out your gallbladder. I don't know how successful it is, but notice, anybody who's had their gallbladder removed? I know a lot of people who've had their gallbladder removed because our diets are terrible in this country. So maybe cleansing diets wouldn't be the worst thing for most of us. But it is part of the degradation process for cholesterol. So somehow lowering your cholesterol is something most of us try to strive for when we get into poor health, because that's usually one of the things they look for. And I say most of us. Do we care before we're like 40 about cholesterol? No. So, but we probably will someday. So going further into cholesterol, we'll talk about lipoproteins. 4 different classes of lipoproteins. There's actually a couple others that we won't hit too hard, but the 4 that we will talk about: chylomicrons, VLDL, LDL, HDL. Which are the two that are more commonly talked about if you do go to your doctor and having some cholesterol issues? HDL and LDL. And what do we commonly call these? Good and bad. Who's good and who's bad? HDL is good, LDL is bad. Now, why is HDL good? Yeah, it's scavenging cholesterol and taking it back to the liver, getting it out of your bloodstream. So why is LDL bad? So it's doing the exact opposite. It's taking it from your liver and giving it out to everybody else. So and the idea is to get it out of your bloodstream, right? Because it can lead to atherosclerosis and things of a sort, hardening of the arteries. Cool, but that's your good and bad cholesterol. In fact, why don't we just focus on those for a sec? Your LDL, its job is to take cholesterol out to the tissues, away from the liver. It's 45% cholesterol, 70% of your plasma cholesterol is in the LDL form. So you have much more LDL typically than HDL. So when you go to the doctor, he's like, yeah, your LDL levels are too high. Notice you're never going to get your HDL levels probably higher than your LDL. So that's not the goal. It's just to get the ratio in a little better place. So your HDL is much greater concentration of protein, only 20% cholesterol in your HDL. And again, its job is just to scavenge, grab cholesterol where it finds it, and take it back to the liver to get rid of it. If you notice, what does HDL actually stand for? High density. What does LDL stand for? Low density. VLDL? Very low density. So if you look, so HDL is the highest density, but it is the smallest. So the highest density one is the smallest. It's the most compact as well. So don't get it backwards. A lot of people think high and low. The high must be big. It's not true. The highest density one is the smallest. The low densities, as they get lower and lower density, they get larger and larger. Cool. Your VLDL and your chylomicrons. Let's talk about those now. Those are not usually on your cholesterol report with your doctor. So chylomicrons, what's the point? So we brought it up earlier, but yeah, these are when you take like fat in your diet. This is getting ready to ship that fat off to where it needs to go. So notice it's almost all lipid. So 85% triacylglyceride. So these are big lipid bodies, if you will. Only a little tiny bit of protein, mostly lipid. Cool, and usually they're involved in taking fat from your diet out to the tissues. Either for use or storage, but most likely for storage. VLDL, very low density. So 50% triacylglycerides, 20% cholesterol, and cholesterol esters. And its point is to transport plasma triacylglycerols. It's synthesized in the liver, and as it starts delivering out triacylglycerols, it gets a little smaller and a little smaller. So, and eventually turns into LDL. Question. The largest so, I honestly don't know. I can tell you the difference between VLDL, LDL, and HDL, but chylomicron's the largest? Sweet, now you know. Chylomicron's the largest. So if you look then, they're getting smaller as we go down. Cool, couple other things. If you look at both VLDL, its main protein is ApoB100. Notice because VLDL turns into LDL, what do you suppose LDL's main protein is? Also ApoB100. So, and he's just a convenient protein to have because that's involved in LDL receptor recognition. So that's the way LDLs get recognized in interacting with other cells. HDL's main protein is ApoA2. So, and that's what's involved in binding the HDL receptor so that the liver can take up that cholesterol to recycle it. Cool. Cool. Last little thing in this section. Prostaglandins. It's just kind of a fun word to say. So prostaglandins, a type of eicosanoid. So I guess you could also classify this under eicosanoids. The only one you really went under. Arachidonic acid is the precursor for your prostaglandins. You can make a boatload of other prostaglandins, and I don't think that's really the most important thing. One thing that is important, though, is that the COX enzyme, this is the major regulatory step involved here. So if you look, prostaglandins, so back when I took biochemistry, which was a long time ago, let's just say you weren't in high school yet. You weren't in junior high school yet. So it was a long time ago. So, but this was kind of something fairly, little newer than it is today, let's say that. But basically, it is COX here, and specifically COX-2. This is where your anti-inflammatory drugs like ibuprofen and naproxen and stuff, this is where they are acting. So Is the inflammation response a good thing? Sometimes, up to a point. So can it be a bad thing? Yeah, if it goes a little crazy, gets a little excessive, it can definitely be a bad thing. So the idea is that if it's to the point where it could be a bad thing, well then let's take some ibuprofen or some naproxen or something and calm the inflammation down. It is inhibiting this enzyme here. It is the prostaglandins that are involved in the inflammation response. So if I can prevent their synthesis, I kind of prevent as much inflammation response from happening.